Let's see how we can train linear models for classification. The objective here is to learn the decision boundary that separates the positive from the negative points in our data. So the decision boundary is this line here. It separates the blue points from the red points. Now we can do that by learning a hyperplane, which is a plane in an n-dimensional space, so that where it intersects with our original data defined by our features, this creates our decision boundary. So if you can imagine another dimension here, then this is our hyperplane, which cuts through this other plane right at the decision boundary between the red points and the blue points. Whenever this function, so say that this is y, whenever this function is positive, we predict the positive class. If it's negative, then we predict the negative class, right? So all of these points are positive when you project a point on this hyperplane. It will be positive, and the more positive it is, the more positive the model is about that this is a positive point. All right, cool. There are many algorithms that can do linear classification, and again, they all differ in the loss function, and that means they also differ in how they have to be optimized and how they can be regularized. We can roughly divide these into different categories. So there are some techniques which first convert target classes, so negative and positive, to 0, 1, and then just treat it as a regression task. Right? So now the negative points have to be predicted 0, and the positive points have to be predicted as close as possible to 1. One very well-known approach for this is logistic regression, which uses the log laws internally. Another algorithm for this, which is much less popular, is wedge classification, which uses least squares and L2 laws. It's similar in performance. Now, we can also try to find a hyperplane that maximizes the margin between classes. So if we have positives and negatives, we don't just want any line, but we want a line that maximizes distance between the positive points and the margin and the negative points. It's an extra constraint that we put on the model, so hopefully it will generalize better. So this leads to linear support vector machines, which internally use the Hinge laws. We can also use a simple neural network without any nonlinear activation functions. And the well-known example here is a perceptron, which uses the perceptron laws. And finally, we can also use a gradient descent classifier, which uses a range of different loss functions, like Hinge, log, and Hoover. And depending on what you use, you will basically solve the same problem as the ones above, only optimized in a different way, which is often useful when you have very large data sets. Okay, the first algorithm is logistic regression. This one is a bit special in that it doesn't actually want to predict a class, positive, negative, but it wants to predict the probability that a point belongs to the positive class. So it tells you something like, I'm 80% sure that this is a positive point. It does this by first converting the target values, a positive and negative class, to 0 or 1. So all the blue points, the negative class, are mapped to 0, and the positive class, red ones, are mapped to 1. So you can see this as adding another feature to our data set. So we have a new target feature y. And then fitting a function through there which maps this as closely as possible. Of course, a linear function in this space won't really work, like fitting a straight line here doesn't work. So we'll use another function called the logit function. So the logistic function, sorry, also known as the sigmoid or the S-curve. We choose this one because this maps our domain from -infinity to +infinity to a probability between 0 and 1. Now, this logistic function has this form, so it's 1 over 1 plus e to the minus, and then we have our function f. So this is our linear model. It is shown here by this black line here. This is our linear model f w x. Right. So if you would put that in, say that we have a one-dimensional problem, then this is our linear model, and then the logistic function basically looks like this, and this transforms this black line into this green curve. That's a transformation from a linear model to a non-linear model. The ways that we learn, so we're actually still learning a linear model, only the loss function that we use transforms this first to another domain so we can make predictions about probability. But intrinsically, it's still a linear model. So where our function f intersects with 0, that's our decision boundary. Right? So in this case, it will fall somewhere here. And this happens to be the point where our logistic function has a probability of 0.5. So if the predicted probability is lower than 0.5, we predict negative. If it's higher than 0.5, we predict positive. And so we can see that if we change the coefficients of this line, so if we first of all change the bias, so the intercept, this will move this linear model left and right. And as a result, the logistic function also moves left and right. That's what that parameter does. The other parameter, that's basically the slope of our linear function here, will flatten or steepen our S-curve. So if we make the slope, I have to move it here now. So, it's too flat, sorry. I have to move up. Okay, so now we can make the function steeper. Right, so you can see that my linear function here becomes very steep, and then our S-curve also becomes very steep. And so basically we're looking for the set of weights that optimally goes through these red and blue points. We'll see in a minute what optimal means. Right? That's a loss function. We can first look at this in 2D. Same thing, so in that case our logistic function is a 2D function, and again we can see that it has this S shape, but now it has all this extra dimension, so it's an S-shaped surface, separating, well, which will be high for the red points and low for the blue points, and our decision boundary is basically the plane which intersects the 0.5 line here. In principle, you can choose where you put this threshold. We'll see this later when we talk about evaluation functions. But in principle, you don't have to stick to a 0.5. If you want to reduce false positives or false negatives, you can move this up or down depending on the application. Now, what does it mean to have a good fit? When does this line fit well? That's defined by a loss function, and in the case of logistic regression, this is cross entropy, or in the easier terms, log loss. Now, cross entropy, this name comes from information theory. What it basically does is penalize errors in a smooth way. So say that we have say that true label is 1. Right? Then we want our predicted probability to be also 1, or at least close to 1. If our predicted probability is close to 1, then you can see the blue line here, the loss will be very low. However, it exponentially increases. So if you make, first of all, if you're 0.5, you're not sure at all, then you have a much larger loss function. And if you make a mistake, if you think that there's only like a 10% chance that this point is positive, this loss will get exponentially larger. The opposite is true for, if the true point is a 0, then of course you should predict, if the true label is negative, then you should predict a 0 probability. So if you do that, then you have a low loss function. If, on the other hand, you think there's a high probability of being a positive class, even though the point is negative, then you will get a large component to the log loss. Okay. So the loss function looks like this. So it has p times log q, where p is a true probability, so that's 0 or 1, and q is a predicted probability. That's what's shown here on the x-axis. And we can see that the penalty grows exponentially as the difference between those two decreases. Right. If you would write it down for the binary case, it looks like this. So it's this is the correct class times log the prediction times 1 minus the class times log 1 minus the prediction. Right? And this does exactly what I just explained here. Right? So say that our true value is 1, right? Then this term becomes 1 and this one becomes 0, so we don't look at that. In that case, we look at the log of our predicted value. So the log of, say that the predicted value is 0.7, then the log of this is this value here, which is quite small. Right? If, however, you predict 0.3, even though the true label is 1, then you will get a much larger loss. If, on the other hand, the true class is negative, then yn is 0, so then this falls away, this becomes 1, and we look at, for instance, if this is 0.3, how high this scores on the red curve. So, yeah. And vice versa. Now, sometimes we call this penalty the surprise. So this is sort of the human equivalent of being surprised by something going wrong, right? So say that you think, I'm 50% sure that something will happen. Whether it happens or not, I won't be very surprised. But say that I think I'm like 99% sure that something will happen, and then it doesn't, then my surprise will be very large. As first, if I think there's no chance that something will happen, and it does happen, then again my surprise will be very large. And if my surprise is large, then this is like an important learning experience. Right? So the loss will be high, and I have to correct my weights and biases by a lot. Okay, so this is the pure form of course entropy. In practice, we will often use this together with L2. So we'll add a component here which has the sum of the square weights times our parameter alpha. Or if you do L1, then this will be, of course, plus alpha times the sum of the absolute values. Right? Now there's a whole different suite of techniques or solvers to solve cross-entropy loss. First of all, we can just use gradient descent. This only works if the regularization is L2. Log loss is differentiable, so we can use stochastic gradient descent or any variant of that. And a popular choice for this is again stochastic average gradient. We can also use coordinate descent, both for L1 or L2 regularization. Again, this has fast iterations, but may ultimately converge more slowly, and there is a chance that you get stuck in cell points. In Scikit-Learn, this is called linear, and again, this can't run parallel, so it may not be ideal if you have your mind set on doing this in parallel. There's another thing you can do, which is called Newton-Raphson or the Newton conjugate gradient. What that does is instead of, so you have a convex loss function, you can, instead of just computing the gradient and saying, well, I want to go there, you can actually compute also the second derivative of the loss function. And it's called a Hessian. So the Hessian is a matrix which has basically all the second derivatives of your loss function with respect to two different variables in your loss, for two different weights. So this is expensive to compute. The idea is that if you compute this, you will get the exact direction to the minimum. Again, because this is convex. Now, in principle, you can do that, and that means that in one update, you will get to the minimum. But of course, your data is noisy, so in practice, you do want to attenuate that by adding a learning rate eta. So you will make smaller steps. This version, so this dramatically speeds up the number of steps you need, right? So you can get to the minimum in fewer steps, but again, computing this is quite expensive, right? So I would only do this if you have smallish data sets. And it also assumes that the solution space is convex or near convex, so yeah. Another thing you can do is quasi-Newton methods. It's the same idea as here, but you use approximate techniques, which are faster to compute. And one of these guys is called the limited memory Brodmann-Fletcher-Goldfarb-Shannon method, or LBFGS. And this is actually the default. So if you use Scikit-Learn and if you use logistic regression in most implementations, this is the default solver used. So again, this is an approximate method of this Newton method. Now, which of these should you choose? Well, on the high level, if your data set is small, you can use all of these. If your data set is larger than gradient descent, is probably a good idea. And you could also try some quasi-Newton methods like LBFGS. There's a nice blog post here on choosing different solvers. What this shows, that's an interesting takeaway, is that scaling your data, one, helps convergence. That's not surprising, right? So scaling your data makes optimizing these weights easier, but it also minimizes differences between the solvers. So if you scale your data, then the differences between these isn't really big anymore. So then you may as well choose one which is fastest. But again, there's no hard-cut rule for this. So again, experimenting is a good idea. Okay, how does this look like in practice? So we can find logistic regression in the linear model package in Scikit-Learn. Now, interestingly, while we would expect an alpha parameter, this implementation has a parameter called C, which is the inverse regularization strength. The reason for this is so it is similar to the C in SVMs, which we will see next. Okay, but just keep in mind that the C is nothing else than 1 over alpha. The penalty we can choose between L1 or L2. We can also choose LessicNet, or we could choose to not have regularization, although generally that's not such a good idea. And the solver, again, we can solve the Newton conjugate gradient, LBFGS, linear, or Sega. Sega are actually, the stochastic average gradient, are typically not a bad approach either. So you could also try these. Now, if you increase C, because it's the opposite of what you would expect, if you increase C, you will actually have less regularization, which means it will try to overfit individual points. So let's try this in practice. So I have my implementation here. So I fit this on some data. If I so this is the line I find normally. If I increase C, and you can see that it has two misclassifications, one blue point here and one red point here. So if I increase C, so if I have less regularization, you'll see it starts overfitting because it wants to get every point correctly. And so in the extreme, it will do something like this, just to get this blue point on the right side of the boundary, right? Now, generally speaking, this is not such a good idea because this may be a noise point, so you're probably modeling noise now, and your model may generalize worse actually on unseen data. If you do the opposite, you can also see that the weights get larger. Right? If you do the opposite, then the weight should get smaller, and this curve should get flatter and flatter. And if you take it too far, again, your model will underfit. So you can see, well, this is obviously not a good solution. This is like totally underfitted, just because it tries to push these weights down as much as it can. So you probably want, again, you want to find the sweet spot where we don't underfit or overfit. And again, we can look at a validation set and then optimize our C parameter. If we plot all values for C, again, we can see the situation that we saw with alpha, but now it's the opposite. Now, if C is small, the method is underfitting. If C is large, the method will start overfitting. Although honestly, there's no clear convincing descent here, and that's because the data set is quite small. Okay, again, we can also choose between L1 and L2. So we start with some C closer to 1. Again, if we have L2, we can see that most of the weights will be 0. If we have L2, we can see that the weights will be close to 0, but not exactly 0. So it's the same thing as we saw with Lesu and Rich. And again, we have to, when we choose L1, L2, we typically choose L1 when you want a sparse solution, when you want to eliminate features, and when you want fast predictions. And if you want to have both, you can also use a LessicNet. Another way to do classification this way is using rich classification. This works by, the loss function is exactly rich, And we can do this if we map our target variables to -1, 1. Right, so if we have, so if our negative points are -1 and positive points are +1, then computing this, so say that our true outcome is 1. If your model predicts 1, then the error will be 0. If your model predicts -1, then this error will be non-zero, and then you square it, and that contributes to the ridge loss. So this is very similar to what we saw before bridge. And again, we can use the same solutions to solve this. There's a closed form solution called Gillespie. There's gradient descent variants like conjugate gradients and stochastic gradients. And again, you can use Gillespie for the small data sets and gradient descent for the large data sets. Now, a second type of model which is very useful are support vector machines. The idea there is that you find a hyperplane that not just separates the green points from the red points here, but it also maximizes the margin between them. The idea there is that if I have a point, a green point here, and now I have another point nearby here, this decision boundary here will break this as a red point. And having a red point so close to a green point, that's probably not a good generalization, right? If you have a point close to a green point, I would expect that the predicted class to be the same. And this decision boundary does not allow that. If instead we fit the function so that the margin between the positive and negative examples is as large as possible, then this won't happen. Any point close to the green one will be predicted green, and all the points close to the red one will be predicted red. Right? That's the whole idea. The support vectors are training points that are on the margin, and these completely define this margin, and they are sufficient to make any predictions. So if I have a new prediction, say I want to predict this point here, I simply have to look at how far this point is and what their labels, the correct label is. Now each of these will get a weight assigned to it after modeling. We'll get back to how that happens, but that's the basic idea. Right. So how can we maximize this margin? So what's the formulation of this margin exactly? If we look at this green line here, this is our y, and our y is basically x1 times w1 plus w0, right? So that means that this line here has slope w1. It intersects at w0, and at this point this value has to be 1. Right? So in that case 1 equals x1 w1, or w1, sorry, x1 equals 1 over w1. Right? This is basically this distance here. It's 1 over w1. In n dimensions, this will amount to x is 1 over the 2 norm of w. Now we want to find the way to maximize this, right? And we can do that by maximizing the square of this, of the 2 norm, right? Now this means that we have a problem which is quadratic, right? Which is easy. But we also have the constraint that all the positive points must be on the right side. Right? And this extra constraint is a linear constraint. So we're dealing with a convex problem f. So you want to find the optimum of this function. And with the constraint that every point that we find should evaluate 2 points on this side of the red line. And this combination means that the solution will be this set of weights. Right? This Wi and this W2. That's our solution. Now, this is an established problem which is called Lagrange, which has a solution called the Lagrange multipliers. That solution has 2 forms. It has a primal and a dual objective. Let's first look at the primal objective, because it's probably more intuitive. So this works by assigning a dual coefficient. It's called a dual because we assign it to each data point rather than to each feature. Right? So these are basically weights for our data points. Now, these weights define how much each individual point contributes to the weights W. So we define the weights W as the sum of the correct sign. This is +1 or -1, depending on whether this point is classified positive or negative. And then AI is how much this point influences the overall weight. Right? It's defined like this. These weights have to be positive, and they also have to sum up to 1 when multiplied with the correct sign. Right? So summing up all the positive. So this will be positive for the positive points. Right? Then the last function here so what we want to have is that the predictions are correct, right? So this should evaluate to something positive if the correct class is +1. Right? If it does that, then this is positive, and this term is basically how good the fit is, and the loss will be minus this value. So if we find weights so that the predictions are correct, then this term will be large and the loss will be low. Okay. So basically we sum up the predictions of all the points weighted by the influence of every point. If it's a correct prediction, this goes up. If it's a bad prediction, this goes down. And then the loss is basically the sum over all of these. So if you find a good set of dual coefficients, this will lead to a good solution. We also want to, of course, optimize our convex objective function, and we also want to keep those weights small if possible. So that's a primal objective. There's also a dual objective. The derivation of this can be found in the elements of statistical learning or in many machine learning courses. We won't go into how is this derived, but the basic idea is that while this is a solution in the space of the weights, this is a solution in this space of the dual coefficients. So there's no weights here anymore. This is solved entirely in the space of the dual coefficients. So that's why it's called a dual solution. If you look at this formula, if you look at this formula, or this loss function, first of all, we see that here we're dealing with a dot product, xi, xj. So what this loss function does, it looks at every combination of two data points, training points. If those two are close together, this is the dot product, right? So if we have xi and xj, and they are close together, then this dot product will be large. If this is large, we expect that they also have the same class, right? So this is a class of point I, this is a class of point j, this is the weight of point I, the weight of point j. So if we have two nearby support vectors with high weights ai, aj, and they have a different class, that's bad, right? So you have 2 points nearby, but they have a different class. So that will increase our loss. If they are the same class, then this will decrease our loss. Okay, so it increases if nearby support vectors which high weights have different class. It increases, first of all, yeah, with the number of support vectors and the weights are. With this sum is not done over the combination of all possible points, but only over the support vectors. These are the ones which have an a value, a dual coefficient, which is non-zero, right? So this will not be done for every possible combination, but only for every combination of the support vectors, right? So we want those support vectors to either be on the right side. So we don't want two support vectors nearby to have a different class. And that's it, basically. This can be solved with quadratic programming. And there's a very well-known solution which is called sequential minimum optimization. It's an iterative technique that allows you to optimize this. As a side note, whenever you have a loss function in which the inputs x only occur as a dot product, that's a special case, and then we call this loss function kernelized. In the next lecture, we can see that this has some very nice properties. Okay, let's look at the example result. So we have red points, green points. We've learned our support vectors, and so basically what the model returns is the support vectors and their weights. So we have one red support vector with weight 0.62, and we have two blue support vectors. This one is a larger negative weight, and this is a. So this is actually y I times ay, right? So it's the weight. The weight is always positive, and then we put minus here if the correct class is negative. Right. Now, if you want to make predictions, then we only need to look at support vectors because the other ones have no influence on our weights. So our support vector machine is completely defined by support vectors and their coefficients. And if we know the dual coefficients alpha, we can find the weights as per definition, right? It's this function here. And then we can, if we have a new point u, we can just compute the dot product between w and u plus the bias. And then we can look at the sign. If this is positive, then we predict positive. If this is negative, we predict negative. Now, if we look at this more closely, and if we substitute w for what it represents, right? So alpha times the class times xi. And we know that this is a dot product. Then this term is basically the closeness between the vector xi and the vector u. With the correct class and weighted by some dual coefficient. Now, this reminds us of something because this is very close to k-nearest neighbor. It's not pure k-nearest neighbor, but it's a weighted version of that. Right? So weighted k-nearest neighbor is a generalization of k-nearest neighbor where every point has a weight. So if you want to make a prediction, you look at, so you have a positive here with weight 0.8, for instance, and we have a negative here with weight 0.5, right? What we do is we look at all our neighbors and we weigh them by the weight they have and by how far away they are. So if they're very close by, they have more influence. If they're far away, they have less influence. Right? So this is by using some similarity function or some inverse distance function. Right? This does the same thing. Right? So the dot product tells us how similar those 2 points are, how close they are, and again, weighted by the weight of that point I. So again, if you have a point U and we have multiple x's, we basically sum up how similar they are, computed by the dot product. So this one will be more similar, this one less. And the weight of each individual. So this one has a weight of, let's call it 1. This is 2, has a weight 2, and this is 3, and we weight 3. And summing up, we then make a decision. So what the SVM predicts is basically nothing else than a weighted k-nearest neighbor. Right? And this is also how SVMs predict in practice. Right? So the main difference with normal KNN is that with normal KNN, normal weighted KNN, we would have to look at all the points. With support vector machines, we learned which are the support vectors. We only have to remember the support vectors, and all the other points we can forget about because they don't influence any predictions. And the other difference is that this distance function is, the similarity function, sorry, is an inner product, the dot product here. But the principle is the same. So if we have some positive support vectors with a weight, and we have a negative support vector with a weight, we don't even need to know where this boundary is. We just, if we want to predict where this point is, we just compute the similarity between those points, which will be done by computing the dot product times the weight of the point. And we do that for all the other ones. And again, if it's nearby a point with a high positive weight, then this point is likely to be positive, and vice versa. Now, all of this assumed that our data was linearly separable, and of course, real data is typically not. So in that case, this hard margin maximization doesn't work because our constraints would contradict and we won't find any solution. We can, however, relax this constraint by allowing some error, see, so that say we have the decision binary and we have our margin then it is allowed that a point falls within the margin, or then this will incur an error key. So say this is the positive one, this is the negative one. If a positive point falls here, it has a small error key. If it happens to be here, well, then this key will be very large. Right? So this is basically a penalty for crossing the margin. This is different from like pure 0-1 loss, right? Because pure 0-1 loss, you would only get a penalty if you cross the boundary. Here you already get a penalty if you cross the margin. If you would write that down, it would look like this, right? So if you have if the true label of a point is 1, we're looking at this blue curve here, and this is the margin, right? So if you're on the right side of the margin, this is the decision boundary. If you're on the right side of the margin, you're fine, and your loss will be 0. If you have a positive point on the wrong side of the margin, you will get a small error. If you are on the wrong side of the margin, you will get a much larger error. Vice versa, if you have a negative point, you will get 0 penalty if you are on the right side of the margin, a little bit on the wrong side, and a lot if you are on the wrong side. This loss function we call hinge loss, because it's like a door hinge, basically. And then, yeah, assuming we want to both maximize the margin and minimize the number of errors, this is then our final loss function. And again, we want to attenuate this with a hyperparameter c, which is like a cost for how bad we want to weight these errors, right? So if c is large, it means we are very angry, very concerned about these errors. So that will strongly influence the loss. If we don't care so much about some misclassifications, we can make c small, and this component becomes much smaller. The nice thing is we can still solve this with quadratic programming, so we don't have to do anything special for it. Now, if instead of taking the sum of the errors, like here, we take the square of the errors, we get another algorithm called least square support vector machines. And it's the same loss function. We only replace the sum of the errors by the sum of the squared errors. This results in something called squared hinge loss. If you plot that, then again we see that up to the margin, we get 0 error. But if we enter the margin, we will get slightly. If you're just on the other side, it's still very small. If you are far away or on the other side of the boundary, then of course this error increases very fast. So this can also be solved with Lagrangian multipliers. It's not quadratic programming. It's a set of linear equations this time, but it still can be solved analytically. This still yields support vectors, but while in the normal SVM, we get a sparse solution, so we only get a few support vectors with non-zero dual coefficients. With least square SVM, we don't get a sparse solution, so we get many support vectors with small weights. But there exist some proving techniques which do allow you to remove the points which don't influence the decision so much. And in that case, you can still have a sort of sparse model. Now, what's the effect of the C parameter on the margin? So the normal SVM's Hinge loss acts like an L1 regularizer. Okay? And since C is the inverse regularization strength, so the inverse of the alpha and less so, it means that if we have a large C, we'll have fewer support factors, a smaller margin, and more fitting. So this is like having a large alpha value. If alpha was large, many coefficients were 0. Right? Similarly here, if C is large, then all the weights of the points will be 0 except for these 3 points here. Right? If we relax C, so we have a smaller cost for a smaller penalty for errors. This will mean that fewer of these 2 coefficients will be 0, so there will be more points. And so basically every point in the margin is a support factor. Okay? And so this gives us wider margins. And hopefully this also means less overfitting. But again, the correct value is not known beforehand. You have to tune that based on your data. The same thing happens for non-linearly separable data. So again, if I have a large C, I'll get fewer support factors. If I have a small C, I will get a lot of support factors. And if it's even smaller, maybe all your points are support factors. And again, large C can lead to overfitting, right? So if I increase the C too much, then it will start fitting individual noise points. And while small values will lead to underfitting. How can we run SVMs in Scikit-Learn? There's different versions we can use. So first of all, there's a linear support factor classifier, which is faster for large data sets. It allows you to choose between solving the primal or the dual. So remember that the primal basically learns a set of weights, while the dual learns a set of coefficients. So if you have a data set with a lot of data points and fewer variables or fewer features and there's fewer weights, the primal is interesting, right? Because then you have to learn much fewer weights. If you have 10,000 data points, you would have to learn 10,000 dual coefficients, right? So in that case, the primal is easier to compute. This implementation does not return support factors, it just returns you the coefficients and the intercept. So the weights and the bars. There's another version called support factor classifier, SVC, and this, if you want to have a linear model, you have to say kernel is linear. This one also returns support factors and the dual coefficients. Now, this also allows kernelization, so we can change this linear. We can change this linear model into a nonlinear model. But we'll see this in the next lecture. But the downside of this one is this scales quadratically, at least quadratically, and in worst case cubically, with the number of samples n. Right? So it's not the fastest method. And then we have linear support factor regressor and the normal support factor regressor. These are variants for regression. And again, this means that we want to learn a function so that all the points are within a margin epsilon from the predictions. And every point within this margin gets 0 loss, and every point outside this margin gets a larger loss. This is an example of running SVM. So we load it, choose the kernel, we fit it, and then we can look at the support vectors and the coefficients for each support vector. Now, you can also solve SVMs with gradient descent, of course, which is nice if your datasets are very large. Right? So in that case, the programming solution is not feasible anymore, and we want to use SVM. Now, the squared hinge is differentiable. So the least squares SVM has no problem. The normal SVM uses hinge, which is not differentiable, but it is convex. So it's similar to the lasso situation. And again, it has a sub-gradient. And then the derivative of the hinge with respect to some weights, Wi, is 0 if it's on the right side of the margin, and it's 1 minus the class times x. So if you go into the margin, then you will increase linearly. This will be negative for if the class is positive, and positive if the class is negative, and so on. So this is the case for I is 1, and this is the case for I is -1. Okay, so, and just because we have this, we can compute gradients. It will be either 0 or non-zero, and then we can use stochastic gradient descent or any variant to solve this. Now, because the derivative of hinge loss is undefined, it's defined everywhere except here, 0.1. We have some smooth versions. So you have already seen the squared hinge loss. So the normal hinge loss is the blue curve here. So it has this hinge. Squared hinge is, again, it's flat until 1, and then it grows in squared fashion. There's also something called the modified Huber loss, which is the same idea of the Huber loss in regression, which is that it is identical to the squared hinge loss up to 0.0, and after that it becomes linear. And then finally, just for reference, I also plot here the perceptron loss. The perceptron is a bit special compared to other methods because it will not penalize any prediction that's not sure. So if your model is not sure of its predictions, right? If the y value is smaller than 1, or if the predicted probability is smaller than 1, then you'll get at least some error, some loss for that point. Perceptron instead says, I don't care. If you're not sure, I will only add a loss if your point is actually misclassified. Right? So it's like Hinge. It's exactly the same as Hinge, only the Hinge happens at 0 instead of 1. Okay. Now, is this a good idea? Actually, no, this is not such a good idea, and the perceptron doesn't work so well for that reason. Now, what is this perceptron? As you probably know, this represents a single neuron in a simple way. So it has inputs. So it has the normal inputs x, and this is the node. All of these inputs have a synaptic weight, and basically what we want to learn are these weights. Now this also has a bias, W0, and this is often represented by adding another input 1 so that we can learn this as another synaptic weight. This node outputs basically the dot product of W and X, so it does X times, so 1 times 0 W0 plus X1 times W1 plus X2 times W2 and so on. So it, again, this is exactly the same as linear model. Y is W1 times X1 plus W2 times X2 and so on plus W0. So what this node outputs is exactly the same as linear model. To make a prediction, we pass this through an activation function. So if the total sum of the activations is larger than minus W0, then we predict +1, and otherwise we predict -1. Right. So this W1 is basically the bias. It defines where this threshold lies, given your data. Yeah, and these weights, they can be learned with gradient descent or with stochastic gradient descent using the Hinge zero loss. And this one only updates in the classification. So if you look at the Hinge zero loss, this is the same as Hinge, only this has a 0 instead of a 1. And here it's outputs 0 if it's correct. It outputs minus the sign of the correct prediction times xi if it's on the wrong side. So if it makes a wrong prediction. So this used to be 1 for Hinge, now it's 0 over here. Now it's maybe not entirely clear. What this does is this corrects the output by 1. So if the perceptron predicts negative while it should be positive, the weights are updated so the output goes up by exactly 1 and vice versa. If you don't see this, so y equals, let's make it simple. So y equals x times w, that's the dot product, plus w0. Right. Now, if we make a mistake, we will update this weight. So now, after this next iteration, I equals x, and w becomes the previous w minus the sign of the correct class times x plus w0. This equals x dot w minus the sign x dot x plus w0. The dot product of the vector with itself is 1. So that means that this is equal to x dot w plus the bias minus the sign of the correct output. So if we have a wrong output and the class is positive, this goes down by 1, and if the correct class is negative, then this goes up by 1. Right. Okay, now finally, all of these models are binary. Now, what do we do if our problem is actually a multi-class problem? Right? Say you want to predict a number or handwritten letter or something like that, right? So if you have multiple classes, how do you do that? So there's 2 ways of doing this. The most common way is 1 versus rest, or 1 versus all. So what we do here is we learn one model for every class versus all the other classes. So first we learn a model that separates the red points from all the other points. then we learn another model that separates the blue points from all the other points. And then we learn a third model which separates the green points from all the other points. And then if you have to make a prediction, we will ask each individual model what they think. So we will get a quite good score for red, because on this side of this red line, you will get a smaller positive number for blue, and it's on the wrong side of green, so we'll get a very negative value for green. So this means that it has a larger value for red and for blue, so this will be red. And if we evaluate that for every possible point, we can see that the decision boundaries that you will get in this way are like this. Right? So every point on the right side here will be more red than blue, so it's weighted red. And other way, like every point here is obviously green. If you stay on this side of the line, then this will be more green than red, and this is weighted green. Okay. And there's one alternative, which is called 1 versus 1. And what that does, it learns a binary model for every combination of two classes. So we take two classes, we forget all the other classes, so we throw the data away, and then we build a model on the remaining data, which is binary. And we do that for every combination, which means we have C times C minus 1 divided by 2 binary models. Now, this is a lot of models. If for instance, if you have 10 classes, then this is 45 models. Right? But every model itself is cheaper to train because it only looks at a part of the data. Right? So if you have 10 models and they're equally balanced, then if you have only 2 classes for each model, it means you have only 20% of the data, right? So you have more models, but they're faster to train. And then after you train all these models, you classify each point with a majority vote. So you let all these models make a prediction, and then the majority vote wins. Now this can also be a soft vote. So instead of having +1, -1, you can also ask each model to give you probability or decision value, and then you sum up all the probabilities of each class, and then the class with the highest probability wins. Okay. When do you want to use that? Typically only when you have a data set that does not require much data. Right? So if you have a model that learns well on small data sets, then this typically works better than the 1 versus rest approach. But because you train these models on significantly less data than with the other approach, it does require that these models can learn efficiently with few data points. And so this is typically used for small vector machines or Gaussian processes, but not for the other models. Okay, that's it. So now a short overview. So you've seen quite a few models. We've seen these squares, which is a regression function which uses the sum of squared errors as a loss function, can be solved with a closed form solution or stochastic gradient descent, and has no regularization. We have rich, which adds this L2 term to the loss function. Can again be solved with a closed form solution or stochastic gradient descent, and has a parameter alpha to control the regularization strength. We have lasso, which adds the L1 norm. This has to be solved with coordinate descent, and again we have this alpha parameter for controlling the L1 strength. ElasticNet has both L1 and L2, uses coordinate descent, and has alpha, but also the L1 ratio or rho. And then more generally, we can have the stochastic gradient descent regressor which can emulate all of these and solve them with stochastic descent. And next to these, we also have Huber loss for outliers. We have epsilon sensitive to mimic support vector machines. And we can add L1 or L2 to each of these. And for regularization, you have to choose between L1 or L2 and then tune alpha. For classification, we've seen, first of all, logistic regression, which uses log loss with a choice of L1 and L2. This can be solved with stochastic descent or with core descent or anything else. Here we have to choose between L1 and L2, and we have to tune the alpha parameter. Risk classification, which is a special case. So here we have the sum of squared errors plus L2. This can again be solved with Lagrange with closed form solution or stochastic descent. And again, we have to tune alpha. Then we have a linear vector machine, which is the only one which does not have an actual linear function, but which learns support vectors. The loss function is a Hinge loss. It can be optimized with quadratic programming or stochastic gradient descent. And here we have a C parameter, which is a cost for misclassifications. Then we have the least square SVM, which uses a squared hinge and can be solved with linear equations. We have the perceptron, which uses the hinge through 0 and has no regularization. And we have the more general sort of stochastic gradient descent classifier, which has a choice of loss functions. Again, we have log. This emulates logistic regression. We have squared hinge, which emulates the Squares SVM, or normal hinge, which emulates linear SVM. And we also have modified Huber for outliers. So these can all solve the same objective as these other methods, but the solution optimization is differently done. Okay, and finally, linear models. So they're very good for large data sets. They scale quite well. They're also very good for high-dimensional data sets because if you have many dimensions, you have many degrees of freedom, and you can fit a linear model which still learns a lot of relationships between different data points in high dimensions. It's not so good for low-dimensional data because it's linear. It cannot learn any complex relationship in low-dimensional space. We can use linear models to also fit non-linear or low-dimensional patterns, and we'll see this later. So first of all, we can do preprocessing. Right? We can use polynomial Poisson transformations. We can use, well, this is a kind of generalized linear models. Another kind is kernelization. Regularization is very important. We have to tune the regularization strength, alpha. We can choose between L2, which is rich, which gives you a good fit, but sometimes it's sensitive to outliers. We have Lasso, which very nicely gives you sparse models. So this is good if you want fewer features, because then the model is more interpretable, and because it's also fast to predict. Right? If your model only has a few features in it, it's fast to make predictions. ElasticNet allows you to trade off both, which is useful, for instance, if you have correlated features, which L1 will randomly remove, while having this trade-off allows you to keep both of them. Most of these can be solved with different solvers. Some of them have closed form solution or have quadratic or linear solver. All of these can also be solved with gradient descent, and this is typically useful if your data set is larger. Now you can still choose between variants. There's like normal stochastic gradient descent, there's covariant descent, there's stochastic average gradients or conjugate gradients. These typically lead to similar results, although sometimes you can get convergence with one and not with the other, depending on your data set. And if you have multi-class classification, you can do that with a one versus all approach, or with a one versus one approach in case of support vector machines, or yeah, or Gaussian processes, but that's not a linear model.